right, thanks, Charlie. Yeah, session 7 already. Well, it's been a long few days, but still have a few more sessions, so keep the energy levels up. So the next sessions around storage and IBRs. It's as you'll see, it's a variety of different topics under that larger umbrella of kind of storage. We talk about storage a lot at these conferences, increasingly over the last few years, whether it's batteries, long duration storage, new technologies, pumped hydro. So really focusing on some of the different aspects of that. And so we have a variety of speakers from across the world representing different interests and backgrounds. What we're going to do is each speaker will have about 15 minutes. We're going to take all the Q&A at the end. So do keep your questions for individual speakers or for the entire panel for the end of the session here. Without further ado then, this is Mr. Sun Yu. He's a Vice Director of the New Energy Department of Northeast China Power Grid Dispatch Center. He engages in new energy operation and management in the Northeast China Power Grid. Mr. Yu.
Good afternoon. I'm glad to be here to share the experience of development and application of energy storage in Northeast China Power Grid. First, I'll talk about the general situation of the Northeast China Power Grid. Northeast China Power Grid, NCPG, is one of the 6 regional power grid of state comparison of China, SGCC, covering 3 provinces and 1 region, serving population of 122 million. NCPG is connected with North China Power Grid and Ras Power Grid by HVDC lines. By the end of 2022, the total installed capacity is 189 gigawatts, with thermal power being 55% and the new energy wind with solar being 35%. By the end of 2022, the maximum power load in the NCPG was about 74 gigawatts. The installed capacities of the new energy was about 65 gigawatts and plan to increase to 131 gigawatts in 2025. In 2022, the power generation from new energy was 129 terawatts hours, accounting for 22.5% of the total generation production. In power system operation, the maximum in state nature share of the new energy in electric load was reached 56%, with the goal of carbon peaking and carbon neutrality in China. There will be continuous fast development of new energy in NCPG. As the penetration of new energy increases and the share of coal-fired generation decreases, and their flexibility is being exhausted, energy storage will play an important role in the future power system. Second, I'll talk the energy storage in Northeast China Power Grid. Pumped hydro, thermal storage, electrochemical, flywheel. At present, there are 4 pumped hydro stations in operation in NCPG with a total capacity of 4.1 gigawatts. In 2022, the pumped electricity of pumped hydro station was 5.1 terawatt hours. From 2023 to 2025, the plant's new installed capacity is about 3 gigawatts, with a total installed capacity of 7.1 gigawatts by 2020. By 2030, the installed capacity will reach 10.5 gigawatts. These 3 figures show typical operation of pumped hydro in system. The pump hydro power station in China adopts a two-part electricity pricing mechanism and mainly used for peaking regulation, frequency regulation, phasing operation, blackout start, emergency, standby, and so on. Thermal power plants consume surplus new energy for power generation by installing electric power boilers with thermal storage. By the end of 2022, the capacity of electric boiler was 6.32 gigawatts in NCPG, and 4.2 terawatt hours of new energy was consumed in 2022. In 2014, Northeast electric ancillary service market was established. Thermal power capacity account for a higher proportion in NCPG, and their flexibility is low. Through the market mechanism, promoting the flexibility modification of these units, the integration of new energy in the system has been greatly improved. The modification potential of coal-fired units in NCPG is limited in the future. There are 14 electrochemical energy storage power stations in NCPG with a total installed capacities of 288 megawatts and 92 megawatt hours. Generally, they can be divided into two types: large-scale independent storage, such as Dalian fluid energy storage, wind, solar plus energy storage, such as Tongliao lithium-ion storage. The construction of the national demonstration project of Dalian flow battery was approved in 2016 with a total capacity of 200 megawatts and 800 megawatt hour. The first phase of the project had already been in operation with a capacity of 100 megawatts and 400 megawatt hour. This is the station picture. It's the technology roadmap of the product. Lithium iron phosphate energy storage, the main type of electrochemical energy storage in China, take a share of 93%. The planned capacity of the Tongliao wind solar storage integrated product is 2 gigawatts new energy, and plus 320 megawatts energy storage. The full capacity is expected to be in operation by 2025. The table shows the comparison of the electrochemical energy storage performance. Electrochemical energy storage is now in the state of demonstration. It mainly used for peaking regulation, frequency regulation, accident backup, black start, and so on. Currently, there is a legal effective market mechanism. Key technology innovation are still needed. For example, life cycle battery recycling and safety. Flywheel energy storage is mainly used for frequency regulation and water inertial response. Typical application one, flywheel combined with wind turbine to provide primary frequency regulation and water inertia. Typical application two, flywheel combined with electrochemical energy storage to improve frequency regulation of wind field. Conclusion. The fast development and high penetration of wind and solar in the system pose great challenge to power system operation. Pumped hydro storage has already made great contribution in NCPG. New pumped hydro stations are being planned and under construction. At the same time, pumped hydro storage development is constrained by site selection, long construction period, and possible higher cost in the future, which give comparable advances to new type of energy storage, such as electrochemical energy storage and flywheel storage. Projects of electrochemical energy storage flywheel are now constructed, with some being pilots and some being meditated. With their technology innovation and continuous reducing costs, this new energy will play a big role in system operation. Policies and measures to support the economic of this product are yet to be implemented in China. Thank you.
Thank you, Mr. Yu. And again, we'll take questions at the end here. We'll wait and do all the questions at the end of the panel so we can get through each of the speakers first. So our next speaker, if you don't mind handing the microphone over. You'd have seen Babu last night at the award ceremony. We received an award for a lot of his work on energy storage. He's a senior scientist at Sandia National Labs from 2015 to 2022. He was head of the Energy Storage Technology and Systems Department and Program Manager for Grid Energy Storage at the lab. Earlier, as a corporate fellow at MEMC Electronic Materials. He's a fellow of the IEEE, distinguished lecturer of the IEEE Power and Energy Society, and served as chair of the IEEE Power and Energy Society Energy Storage and Stationary Battery Committee. So, great person to talk about long duration energy storage.
Okay, thank you, Aidan. I think have a good segue into the long duration after the last presentation. What are the planning implications and for storage and IBRs, and long duration storage is a new thing coming up, and what are the challenges we have? What are the different technologies? What needs to happen? So, what is long duration storage? I think people look at the definitions. DOE thinks it's 10+ hours, and others might think much longer, right? So we are just beginning to talk pretty seriously about long duration. And currently, majority of the storage that we are deploying quickly is all battery based and roughly 4 hours. Maybe 8 hours is coming up using lithium-ion batteries. We are not that far off. So anything lithium can do is no longer long duration. So you're looking at maybe 10+ hours quickly, okay? And for the 10+ hours, there are very few commercial contracts or available technologies that can do all the things that people are anticipating. So we have a challenge. We don't have a ready market, and even though we are anticipating that there is going to be one. So what is driving long duration energy storage? I think, I don't have to go into those, but I think, we all know that we are looking at deeper decarbonization of the grid. That's one. Things are coming up on the reliability side and the resilience of the grid once we go to the more renewable into the mix. And then there is a societal acceptance that we do need to decarbonize, and climate change is real. And how do you get there? And that requires some level of longer duration storage. And so I think, things are happening, and people anticipate that we do need long duration storage. The question is, what type, how long, what is the market, and when can we get there? And the other aspect is the electrification of the industry. I think, it requires long duration storage. So what is long duration? I think, as I said, DOE thinks 10+ hours, maybe. And the LDES Council kind of divides it into intraday, multi-day, and maybe longer seasonal, 100 hours plus. And then But you're not just looking at batteries. You need to have, all the above solutions going from battery technologies of various sorts, flow batteries, metal layer, all in the mix, mechanical, pumped hydro, gravity. People are trying different things, thinking about how do you use existing technologies for providing longer duration. And then chemical storage, either you think of hydrogen or some other liquid fuels that are generated from renewables. So these are all going to be in the mix because you're looking for a bigger transformation of the grid over the next 10, 20 years. And the scope of the problem is going to be a lot larger than what we can do with just batteries. But the technology is a gap. We don't really have ready solutions at this point. And we don't really have a market either. Okay, so there is a bit of a catch up that needs to happen on the policy side to drive it, but the market at the same time needs to develop. So both needs to happen before this technology takes off. So as you look at the numbers there, LDES Council thinks we're going to have lots of long duration storage by 2040. 2040 is 15 years out. And the question we have to ask is, what kind of cost reductions we need to get? What are the efficiencies of these new technologies? And what are the markets that needs to drive that kind of a growth? So for a reference, you look at the pumped hydro in Virginia, that's 8 hours, that's 3 gigawatts, right? So you can see the scale. So we're looking at much larger than those. And the largest battery system we have commissioned is 400 megawatts, 4 hours. So gigawatt batteries is no longer project. I mean, these are real projects at this point. So things are happening pretty quickly, even in the battery space. Can we go to longer duration, and what does it take? So what are the drivers? There is, I think, the big driver right now is there is federal funding and some level of policy changes, and some states are more aggressive than others. So there's state-led initiatives coming up. This is mostly in the US side. And then realization that renewables are going to be there and they're coming up very quickly. And how do you operate the grid with a lot more renewables requires some sense of longer duration beyond 8 hours. So what are the big things coming from the government and the federal government? The Infrastructure Investment and Jobs Act, I think you can see there is $60+ billion coming from the DOE. Resilience is a big theme. And that's one area where people see big opportunities for storage. And then specifically targeted is long duration energy storage demonstrations that came from that funding for it came from an earlier time, but now there is a FOA for deploying long duration storage 10 to 24 hours. And the DOE intends to fund 11 projects. That's $350 million with a sufficient cost share. You're looking at $750 million. So $500 million will goes a long way to kickstart some things. Same thing happened with the ARA projects in 2009 when storage was very new. That created the framework for people to demonstrate and deploy new technologies, including lithium batteries, which were fairly new in 2009. And that was a major resource for industry to pick up. And same thing is probably going to happen here. And then the other thing is there is the tax credit for storage, which is going to help make some of the storage, standalone storage, as an asset that is much more bankable than what it was. And that people are projecting that that's going to drive investments in storage and increase how much going to be deployed, anywhere from 50% and above new projects that may come into the picture. Then there is R&D side, demonstrations. Those calls are coming out. I mean, just a few weeks back, there is the LDES for resiliency at a national laboratory site. Small projects, but these are stepping stones to get to the bigger ones. For example, DOE is going to fund 2 projects at national labs, each $10 million to deploy a 24-hour half megawatt type system for resiliency applications at a national lab site. And those are using technologies nearly mature, not ready commercially, but close enough in the next 2-3 years. Can we bring those technologies, demonstrate it at a DOE site, and show that what are the issues are, what the challenges are for these technologies to go to the next step. So I think, there is push in some of these lab calls. But this is still a small effort in many ways. I mean, you look at what does resiliency mean from different agencies. DOE thinks 14 days of resiliency. FEMA thinks 72 plus hours. NEPA has 96 hours. So you have to start thinking, if I'm going to have energy storage providing the resiliency that we're looking of, those are the numbers we're looking at, anywhere from 72 hours to 14 days. So the technologies have to scale much more quickly from 8+ hours of batteries we have, or 10 hours of pumped hydro. And there are other bigger programs with a lot of visibility, some with a significant amount of funding. Long duration storage shot, DOE announced as a target for the next 10 years, with the goal of getting the energy storage part of the cost structure down by 10 to 90% from where it is from the lithium ion. Will it happen? But ambitious target, and that's what we need to do to get to the kind of changes we are looking for. And hydrogen shot, that's already real in some ways with the funding. There's going to be 8 regional centers, each $1 billion, each center. And with the drive to get down the cost of hydrogen to $1 a kilogram. Right now, it's more like $5 a kilogram. Can we get to the $1 a kilogram or somewhere in that range? Then hydrogen can start playing into the seasonal storage mix. And there are a lot of other initiatives, activities that are coming from both these initiatives. Lots of demonstration ideas, initiative to look at, what are the small innovations can we do industry-wise. Storage innovations is a new one to look at some of the underlying fundamental R&D issues with industry. So a lot of things coming up in the pipeline to push LDES. Then you have states. California has been at the forefront for already 3 years now. The first projects they started in 2020. They funded some of the early projects, 11 field demonstration projects using non-lithium technologies, 20+ hours of storage. And they're going for even bigger projects in the next this year with a $380 million funding. And New York is starting with their long duration storage initiative. Smaller effort, but I think they're making a good beginning. They're looking beyond batteries into hydrogen and pumped hydro too. So other states are just beginning to think, don't have any policy framework or support for longer duration in other states. But if what happened in the last 5-6 years with the regular battery-based storage is an example, I think other states will come into this very quickly. So what needs to happen to create a LDES market? Okay, I think we still need to think about what are the long-term system planning that is just beginning to be thought about. I think we as engineers have to go to the regulators and other stakeholders to explain what this technology is all about, what is needed for helping a market to develop, and how do you incorporate LDES into energy markets and operations? I think that part of the planning process, early modeling, market models, all those things needs to develop, and I think that just hasn't happened yet. And higher level models, how much really storage do you need? How do you operate? How do you control? Those aspects are also not totally clear at this point. And then mechanisms to compensate. In the end, if you don't have a project developer to make a project viable commercially, things are not going to happen. So we need to start thinking about how do you actually have some compensation mechanisms beyond resiliency. Okay, so those are the things that needs to happen. And then we have to start thinking about policies. Policies and the regulatory framework always lags behind technology in many ways in some of these things. And that is true for long duration storage, just like batteries, okay? And that only can help to develop a market. And that part hasn't happened. And that's, again, it's going to take time, but that mechanisms needs to happen. And then we also have to think about existing markets. I mean, you have a market for gas. So gas in the pipelines, right? So you have a spot market. How do you think about other commodity markets? Can we bring some of those market concepts to the grid for support long duration is other area. So in summary, I think we all see the need for storage as we look at the decarbonization and moving towards fossil-free grids. And how much is still debatable, but the numbers are pretty large, okay? And the question is, do we have technologies that can scale to the needs? Because, you know, if you want to replace a gas plant, 500 megawatts, right? 24 hours, do the calculation. So everything that you look at in the grid has to scale much bigger. And long duration storage especially has to scale much bigger. So do we have the technologies? And is this technology going to be cheap enough? Unlike, let's say, wind and solar, you don't have scaling laws. In storage, it's all volumetric. So scaling doesn't happen like other technologies. So things are going to cost more typically. But do we have technology which can actually scale and have cycle lives of 20, 30 years to perform? So those are the things that needs to happen. And if you look at what we have today, some of them can participate, but there is no market to push it. And some of the other technologies like zinc air or iron air or some of the other battery technologies, they tend to have lower efficiencies compared to lithium ion. Are there markets? Are there market mechanisms that can support lower efficiency technologies with a larger footprint? Okay, so that's just beginning. I think some of these things, and then things like flow batteries, they can do 12 hours, but right now you don't have any projects to push that technology to the longer duration at this point. So I think, you know, question we have to ask is, does it take 5 years, 10 years to get there? But if you look at history, 10 years ago, we were doing 15 minutes for regulation markets storage. Nobody thought about 4-hour storage becoming very routine. Now it's happening. So as you look at 10, 15 years from now, a seasonal storage based on whatever technology, is it possible? Probably, okay, and likely happen. But the difference between the current existing lithium-based battery technology and long duration, we don't have underlying technologies readily available. Lithium-ion was built on commercial consumer electronics. Now EV is driving it, and the EVs are bringing about 3 terawatt hours of capacity in a year, in the next few years, to support the automotive industry. What is the driver for long duration storage? Do we have a similar driver? It's not obvious at this point. So I think, you know, the work is cut out for long duration storage, both in the technology side, markets, and applications. So with that, thank you.
Thanks, Babu. Next speaker up is Nilesh Modi. You met Nilesh yesterday as well. He presented. Nilesh from AEMO, Manager Operational Analysis and Engineering. Is the second speaker in this session to have received an award last night, though I think you said it wasn't actually for you.
For you, that's correct.
But you've been involved in a variety of different cool projects around understanding system black events, system strength event assessments, system integrity protection schemes, and a lot of other things related to the change in resource mix and energy transition. It's currently focused on power system operations with high penetrations of IBRs.
Thanks, Aidan. Afternoon, everyone. Yeah, hope you can hear me okay now. So what I'm going to talk about is application of grid forming batteries in Australia. First one about Australian Energy Market Operator. So we are a member-based non-for-profit organization. We are independent energy market operator in Southeast Australia, also in Western Australia. We are also a gas operator in Southeast Australia. I often hear this, how big is Australia? So how many of you have not been to Australia? So, quite a few. All right. Those who are from US, this is for you. Yeah, so that's the geographical comparison between Australia and North America. And those who are from Europe, this is for you. Yeah, so that's the size of Australia we are talking about. But that's good for the tourists. For power system engineer, it doesn't even make sense, right? So this is for all the electrical engineer, a comparison between the power system of Australia or Southeast Australia, or NEM, we call it, with some international systems like Texas, Denmark, Ohio, Ireland, Britain, UK. So this is the context of Australian power system. It's a huge, long, radial, and skinny, not really mass. So we have a unique challenges. In terms of grid forming battery, that's the topic of today's discussion. So we have 3 grid forming batteries in operation as we speak now. Now, these are only grid forming batteries I'm talking about. I'm not even talking about or counting grid following batteries. There are many more there. First one is very well known, Dharampul battery, Dharampul BAS, a 30 megawatt battery in a remote part of South Australia, which I will explain you a little bit more about it. Then Hornsdale Power Reserve, often known as Tesla's big battery in South Australia, 150 megawatt in grid forming mode, and the Walgrove battery in New South Wales, 50 megawatt, which came into operation very recently. And I've listed 6 which are likely to be in the grid in near time. So you can see the scale: 50 megawatt, 150 megawatt, 100 megawatt, 50 megawatt, 200 megawatt, Yabulu, and the last one, but not least one, the biggest battery we are expecting is 850 megawatt, 1700 megawatt hour reserve in New South Wales. And on the right side, I just put those batteries on the map so you get an idea that where they are located. These are only the battery where proponent has proposed. They are going to build it and going to come into the market. On top of that, ARENA, Australian Renewable National Agency, funded 8 big batteries very recently. They awarded this award, and out of them, only one is going to be retrofit. So there is an existing battery which they will convert from grid following to forming, and the rest are new. There are some conditions that you need to have financial close by this date, and then make sure you start commissioning and energizing by this and this date. But you can see the size of it. The smallest one I can see is a 200 megawatt battery. So in altogether is 2 gigawatt, 4.2 gigawatt hour battery is funded by ARENA, which will be in operation in near future. Coming back to the operational batteries in Australia, the first one is a Dharampul battery, which is located at the remote end of 132 kV lines. If I can try and find my mouse and can point you here. I'm not sure it's working, but anyway. So that's here. This is where Dharampul battery is. Very tail end of 132 kV line, connected next to the wind farm, supplying local load. This is a grid forming battery. It's in operation since 2018, quite a while. It's very low short circuit ratio, right? Because it's a tail end of the line. It has shown a seamless transition. That's what the people use the word nowadays, from a grid connected to island mode during a planned disconnection of the upstream network and unplanned disconnection of upstream network. It has proved synthetic inertial response. I'll show you that in the next slide. It has a bit short-term overload capacity, 2 per unit for 2 seconds. That is mainly to supply the load. It has shown that it can black start the system, the local network, that I'll show you in the next slide as well. And it is also participating in the System Integration Protection Scheme, SIPS, or Remedial Action Scheme. That's what in North America they use it. Some of the features I'll show you. The next one is its response in an island mode in a frequency control on the left side. So there was unintentional islanding happened at this point in time where battery switched to island mode, not switched to island mode, but it operated in an island condition and controlled the frequency. You can see very tightly it's controlling the frequency. And after 4 hours, we managed to reconnect the system to the main grid. And you can see the frequency difference between an island mode and non-island mode. The one on the right hand side is a separation event where we had a separation of a region. It resulted in over frequency. And you can see inertial response of the battery. You can see in very, very first, probably second or so. You can see that it's responding to a rapid rise in the frequency. And after that, it kind of controls its frequency control ancillary services. So it kind of goes into a FCAS mode, normal mode. But you can actually at least visualize the inertial kind of a response from the grid, from the battery, sorry. The next one is the black start. So this is where it started slowly ramping up. What you call is a soft energization of the grid. And it energized the grid successfully. It picked up the first load, picked up the second load, a second set of load. So it has successfully restarted a small grid. It's a small grid, but it is managed to do it. So that's some of the feature I'm showing of the grid forming Dharampur battery. The next one is Honsdale power reserve power, call it. 150 megawatt battery in South Australia. It's operating in virtual machine mode. It's trying to mimic a synchronous machine. So during steady state, the response is largely dominated by the current source component. And during the disturbance, the megawatt response or the active power response is proportional to the rate of change of frequency. And the MVR response is proportional to the change of the voltage. It's online now. So far, we have seen it has demonstrated its inertial response, which I'll show you in a minute. It's hard to see on the screen, but I'll try and explain a little bit slowly here. There are a lot of two graphs here. Let's focus on the graph on the left-hand side, okay, where the green one is the response. Okay, so I should probably say that this is the one inverter response. So we had a trial of two inverter in a grid forming mode for quite a long time. And while the trial was happening, trial was ongoing, there was a disturbance, frequency disturbance, and we recorded the response from that one inverter. So the one which you are showing on the screen on the left side is the response from one inverter, which is on a virtual synchronous machine mode. The one on the green is the megawatt, and the one on the orange is the rate of change of frequency. So it has, I have calculated it on a 200 millisecond rolling window average. So it's basically megawatt versus rock-off response. And you can see the highest megawatt when the rock-off is highest, or in this case is lowest. And on the right-hand side, I have flipped the y-axis. So it's a little bit complicated to understand. But the y-axis is going from up to down, from up to down rather than from down to up. This is to show that when the rock-off is higher, the response is higher. When the rock-off is small, the response is small. So this is showing that it's responding to the rate of change of frequency. More recently, there was an event. Sorry, this one is the same event, where the top graph is the response from one inverter, which was on a virtual machine mode. And the bottom one is the response from the entire site. That means all inverter, which includes the response of one inverter. This purple one is the frequency. You can see frequency is going down. This was a 25th of May 2021 event. Same frequency over here. The response from VMM, you can see slightly leading than what you get it from the site response, which is on FFR mode, which is a grid following inverter in FFR mode. You can see that it's responding to rates of change of frequency. So when the rate of change of frequency is high, you can get the maximum megawatt. And the maximum megawatt is earlier than your frequency nadir. Okay, so that's actually helping to arrest the frequency. While here, the maximum megawatt is where the frequency is at nadir. Okay, this graph is of same event, where people often say, okay, how can you quantify inertial response? How can we see you are providing inertial response? I got two graphs. Let's focus on the one on the left-hand side first. Is the response from a synchronous machine, a large synchronous machine. On the primary axis is the megawatt. On the secondary axis is rate of change of frequency. Again, I have inverted it. Okay, so when it's actually going up, it's reality the rock-off is in the negative direction. But you can see the response from a synchronous machine. This is the rate of change of frequency is high. You get the more megawatt. As you have a less of rate of change of frequency, you get less megawatt, and eventually the governor kicks in and it drives this response. But at least for a first few seconds, you can see the response is largely driven by its inertia until the governor kicks in and start controlling the frequency. And the one on the right hand side is the same graph which I have shown in the previous slide. And you can see at least for first two peaks, right? It's largely similar. So response from one inverter, of course, this is one inverter only. This is a probably 550 or 600 megawatt of a synchronous machine. But when you scale that one inverter to all the inverter, it's likely for the first one or two peak, you are going to get similar response. Now, this response on the right-hand side is only virtual synchronous machine mode. There is no FFR enabled, right? So there is a caveat there. So that's the inertial response for me. Yes, comparing the synchronous machine, traditional synchronous machine, and virtual synchronous machine or grid forming battery like. This is the model verification of the battery. Maybe I'll skip it in the interest of time. So far I have shown you the real application. Okay, there is no simulation, there is no model accuracy requirement, there is no doubt of the model, all reality. Okay? The next few slides are on the potential grid forming application. So this is based on the desktop analysis. The first one is the systems and supports. Partially I discussed that yesterday. The one on the left-hand side, I show that, okay, if you have let's focus on the right-hand side figure, which is much more easy to visualize. When you have baseline and you have a grid following inverter, a step change in the grid strength would excite this oscillation. And if you have a grid forming inverter sitting very close to that grid following inverter, you can see it is stabilizing this oscillation and you don't see any oscillation. We have tried with the 3 grid forming models. And for the comparison purpose, I have a Syncon as well. So if you install a Syncon, synchronous condenser next to grid following inverter, it kind of provides a similar response. So that's again on a desktop analysis. We haven't seen that in reality so far on the field. And the inertial contribution, this is again quantifying the inertia from grid forming battery. A desktop analysis. What it is telling me that it is dependent on the operating point. As you move towards its maximum operating point, the inertia contribution, which is on y-axis, is gradually going to reduce. You can see the lines are converging towards very small value. It will depend on the overload capacity. It will also depend on the size of the contingency. So if you are sitting here and the size of contingency is 0.5 per unit of the rating, then you get a different megawatt second response compared to what you're sitting here. So it depends on the operating point. It depends on the size of the contingency as well, whether the size of the contingency is generator or the size of the contingency can be load as well. And the last slide I have is the frequency control, how grid forming batteries can help in the frequency control. This is the test system where there is a loss of a generation. If you have all the battery in a grid following mode, okay, with FFR enabled, you can see the frequency goes all the way to 49 for this specific size of the system, for this specific generation contingency. If you have all of them in a grid forming mode, then you can see it's kind of a stabilizing a little bit quicker. At least it's not reaching to 49 hertz. On the other side, this is the response from the battery itself. If you have all of them in a grid forming mode, assuming it's virtual synchronous machine mode, then you can see this kind of oscillation coming up from the battery. That's this graph I'm showing you here. And all of them are grid following mode. You won't be able to arrest the frequency, above, let's say 49.2. But at least you wouldn't have those oscillations coming up on the grid. So there is a give and take, right? So whether we need all batteries in a grid forming mode or all batteries in a grid forming mode, following mode, or in between that too. So that is system dependent. That's my last slide. Thank you very much.
Thanks, Nilesh.
Yeah.
So our last speaker is Jonghwan Kwon. He's an energy systems engineer in the Center for Energy, Environmental and Economic Systems at Argonne National Lab. He's a PhD in electrical engineering from Arizona State, and his research is focused on modeling and analyzing power system operations and planning using mathematical optimization and simulations. And we'll talk about pumped storage in Alaska.
Thank you. Thanks for the introduction. I'm Jonghwan Kwon from Argonne National Laboratory. Thanks for ESIC for having me today. Today, I'm going to talk about our recent study on the prospect for pumped storage hydropower in Alaska. Okay, so PSH is a commercially mature energy storage technology that represents the bulk of United States current energy storage capacity. Right now, there are 43 plants in the US with a total capacity of 22 gigawatts of storage capacity. So with it has high efficiency and long plant lifetimes and make it an attractive solution for longer duration storage needs, particularly as we see a growing penetration of renewables in the country. The PSH offers various grid services that are particularly beneficial in Alaska. Alaska has very unique power system structure. It has two larger independent systems, including Railbelt and Southeast Alaska. They are not connected to each other. And there are over 150 small standalone power systems that are serving remote communities. Oops. Yeah, actually, this is my old slide, which is fine. Yeah, so it has high seasonal variability of wind and solar resource potential. For instance, there is little to no daylight during winter months. And also, the cold climate in the winter time affects typical battery performance. So the goal of this project was to investigate the potential for PSH in Alaska, both in the Railbelt system and the remote communities. So we work closely with NREL, and NREL performed the PSH resource potential analysis as well as the remote community analysis. And Argonne team performed analysis for the Railbelt system, which is the main focus of today's presentation. So the Argonne team performed the simplified long-term generation expansion planning study for the Railbelt system using a least cost generation expansion planning model to assess the possible size, location, and timing of new PSH investment. I want to clarify that this study does not include a detailed integrated resource planning for the Railbelt system or any local utilities, and we don't perform a complicated and detailed reliability assessment in this study, and it's not a comprehensive market analysis that focuses on revenue sufficiency of resources. Instead, our focus was to see the potential for PSH in Alaska under the Railbelt system under multiple scenarios. So we used the Argonne low carbon electricity analysis framework called ELIF for this study. ELIF is an integrated national scale power system simulation framework developed at Argonne, and it includes both long-term planning, expansion planning models for generation and transmission, and also short-term production cost simulation that are linked together under the same data set. So we start with modeling the Railbelt system for this analysis. Unfortunately, the network data for the Railbelt system is not open to the public. So we use the simple zonal network topology using 4 zones, as you can see in the table. So the zones are determined based on the local utilities that serve different regions. And the existing fleet information was obtained from EIA. And total installed capacity, currently the total installed capacity in terms of winter capacity was about 1,800 megawatts. As you can see, it's much higher than their winter peak demand. So right now, the planning reserve margin of the Railbelt system is over 100%. And while typically in the lower 48 stage, we expect around 15% of planning reserve margin. And as I mentioned, the Railbelt system has high seasonal variability for PV and wind potentials. If you look at the right-hand side figure, it shows the PV potential, monthly average PV potential in different regions. As you can see, there's very low PV output, potential PV output during winter month when the Railbelt system is winter peak system. We performed analysis we performed expansion planning from 2025 to 2046 while making investment decisions every 3 years. And we use the planning return margin as, we set the minimum planning return margin at 30%. I know we had great discussion in the previous session about how bad it is to use planning return margin in the capacity expansion planning model. But yeah, I can talk about more in the later slides, but we used 30% as a minimum, but it was not binding at all at the end. And instead of using 365 days in the model, we selected 28 days that can represent the full year. And the plot shows how the selected 28 days represent the net load duration curve. In terms of reliability criteria, this is important actually. So typically, we set operating reserve requirement based on N-1 criteria. But in this study, we use, instead of using N-1, we use N-2, which means we want to make sure that the system is N-1 reliable after losing 2 elements simultaneously. This was recommended by our local advisory board member, and it actually reflects how local utilities operate their system. In addition to that, we enforce the model to procure operating reserves. And when a resource providing operating reserve, they have to be able to maintain that operating reserve for 8 hours instead of 30 minutes that typically we use in the spinning reserve. Instead of 1 hour that typically use in the spinning and non-spinning reserves. The reason is that the network is radial network. So when there is a loss of transmission lines, we want to make sure that the system is reliable, even if we lose a transmission line and lose another generator in the system. And 8 hours is estimated based on typical average outage duration of transmission lines in the lower 48 stage. We consider NGCC with and without CCS, and NGCT, PV, wind, battery, and PSH as investment options. And we obtained the financial parameters for these technologies from NREL's ATB. And for battery, we assume a 10 megawatt capacity with 4-hour duration, and PSH, we assume that it has 100 megawatt of capacity with 10-hour durations. For battery performance during cold weather, we assume the round trip efficiency will be reduced by 10% when the ambient temperature in a region falls below 32 Fahrenheit to compensate the needed thermal management. And as you know, everything is expensive nowadays, but things are more expensive in Alaska. So we apply the additional cost scaling factors in different regions for different technologies. Currently, in the Railbelt system, there are many thermal generators that are being operated beyond their lifetime. So if we allow the model to retire all the units that are subject to retirement, then we will end up seeing huge retirement in the first planning years. So to prevent that issue from happening, we applied the 2-phase approach here. So in the first phase through 2030, we allow the model and we allow the extended operation of older generators and let the model decide the optimal retirement timing of those generators. But after 2030, we enforce the model to retire all the generators subject to age-based retirement. Fuel price in 2022 was provided by local utilities, and we applied the scaling factors for future years. And we have 4 scenarios. In the reference scenario, we assumed about 20% load increase by 2050 from now. And we consider the planned expansion of southern intertie from 75 megawatt to 100 megawatt in 2030. This is already planned in Alaska, so we decided to have that in the reference case. And we considered ITC and PTC. In the carbon price, instead of using ITC and PTC, we applied carbon price at $40 per ton, CO2 ton. The RPS scenario we considered 80% RPS target by 2040 in addition to ITC and PTC. And in the high transmission line scenario, we increased the AK intertie from 75 megawatt to 2050 megawatt in 2040. There are a couple of other assumptions we make here. First, the Fairbanks region currently do not have access to the natural gas. There's no natural gas pipeline from the Anchorage region to Fairbanks regions. But we assume that they will have access to natural gas after 2035. Also, the earliest in-service year for KSH is assumed to be 2030, considering the long construction time. So in summary, this is a summary of the simulation result, and this plot shows the firm capacity or unforced capacity of the new investment under different scenarios. And we see that the railway system needs both a short duration and long duration energy storage in the future under all scenarios. And the results include the PSH capacity between 300 megawatt or 600 megawatt. This is a reference case results. So left-hand side, we are seeing system-wide generation mix in terms of installed capacity, and right-hand side, unforced capacity with planning reserve margin. So I just want to highlight one thing here. So you can see the reference case has huge planning reserve margin. So again, we typically expect around planning reserve margin around here, but we start with about 100% of planning reserve margin, but still see a huge planning reserve margin. There's two reasons. One reason is that we assume that the PSH and battery has 100% of capacity credit. So when you build this battery and PSH, you basically have higher planning reserve margin in the system. That's what we assumed, right? And another reason is that, again, we assume the very high requirement for operating reserve. So the system needs more resources to meet that operating reserve requirement in the system. Now we are comparing the due investment and age-based retirement in different regions in terms of installed capacity. First, we noticed that the short construction period of battery resources result in higher battery investment in early years because we don't allow the PSH investment happening in the first two cases, which does make sense, right? Even if you decide to make an investment decision right now, you don't really see the PSH coming in a couple of years. And the summer retirement of resources, retirement of summer resources in the Anchorage region is offset by new investment in NGCT and battery and PSH capacity in early years. But as I mentioned earlier, the Fairbanks region does not have access to natural gas. So the retirement of thermal resources are actually compensated by additional wind in the system. In the carbon price scenario, we added carbon price to the marginal cost of thermal generators. So it increased the operating cost of those generators. So as expected, we are seeing increased the wind, PV, and PSH investment compared to the reference case. Another interesting finding in the carbon price scenario is that we don't consider ITC and PTC in the carbon price scenario. So it clearly shows the impact of ITC and PTC because we are seeing a substantial decrease in battery investments in the carbon price scenario. In the RPS scenario, we enforce the system to have enough renewable capacity that can supply up to 80% of total demand and annual demand by 2040. And as expected, we are seeing a rapid increase in PV and wind investment. And also this increase in renewable resource investment promote increased investment in energy storage. But as I said, as earliest PSH service year is assumed to be 2030, so we are seeing slightly increased battery investment and in early years, which defer the PSH investment in the result. High transmission scenarios, so we increase the transfer capacity of the Alaskan intertie from 75 megawatt to 50 megawatt in 2040, and that increase the wind investment in the middle zone, and then decrease the wind and NGCT investment in the Fairbanks region, which means the system utilize more resources in the Matanuska region, which is next to the Anchorage region. So conclusion, this study shows that the Railbelt system need both short and long duration energy storage in all the scenarios. And we show that the PSH capacity could be, PSH investment could be included in the optimal generation portfolio between 300 with the 300 or between 300 and 600 megawatt of capacity. However, we show that the location and timing of the investment vary under different scenarios. And also the thermal retirement of thermal generators are replaced or compensated by new NGCT wind, battery, and PSH resources. Also, lastly, the carbon price scenario, we show the impact of the tax credit on especially the battery investment in the system. Thank you for your attention.